Good day, ladies, gents. We're going to be looking at naming and drawing ionic and molecular compounds with Lewis dot structures. The focus is going to be on the naming aspect. We will try to get to the drawing. However, if the video goes too long, I like to keep my videos relatively short. 15-20 minutes. If it gets too long, then I'll make the drawing another video in the future. This is April 7th, or at least it will be April 7th when I post the video. This is for my grade 9 science classes, but anyone who watches it, more than welcome to be here. As always, Mr. Benjamin. I feel like both me writing my name and my face gets worse every time I write this out. But anyways, learning goals for this lesson. We're going to distinguish between anions and cations. Very distinct difference, very important to know for the purpose of naming especially. Then we're going to identify, name, and draw molecular compounds, which we talked about in the previous video what they were, and ionic compounds. There's also one more type, multivalent compounds. Now, these are specifically ionic, but they have a unique case. Let me just rewrite this part out here. It looks like an H. Multivalent compounds. Okay, recall. Ions. Talked about ions previously. An ion is the change in the number of electrons of any atom. Really simple example, oxygen. If I were to draw oxygen's atomic notation, right, atomic notation. Oxygen, I believe, is the 8th element, has a mass of 16. So that means it has 8 protons, 8 neutrons, and if it's balanced, 8 electrons. Okay? Balanced. However, in many cases, well, first of all, we know that protons can't change. Neutrons, if there's a change in neutrons, that becomes an isotope, which is irrelevant for our purposes. But the ions for oxygen, if oxygen were to lose 1 electron, symbol would stay the same. However, we would have a charge on it. Since it's lost an electron, it's lost a negative, it becomes more positive. It becomes positive 1. Erase. Actually, let me erase the whole thing and draw it out underneath. Okay, if it were to lose 2 electrons, symbol would still be the same. I don't know where that line came from. Let's back that up. I'm trying to write with my eraser now. Symbol would still be the same, but my charge would be plus 2. It's because I've lost 2 negatives. If, let me erase all this. I'll write this in yellow instead. We're to gain 1 electron. My charge is now -1. If I were to gain 2 electrons, my charge would now be -2. So these are both ions of oxygen. Difference is you've either lost electrons, becoming more positive, or you've gained electrons, becoming more negative. Okay? We have to distinguish between those two. This is very important for bonding. So we have 2 names. We have cation and anion. An anion is a negative ion, okay? So if we were looking at our oxygen, -1, let's make it -3, which means this has gained 3 electrons. Okay. A cation is a positive ion. So if I use my same oxygen example, 2+, this has lost 2 electrons. The way I like to remember it, cation is positive. If you look at that T right there inside a cation, it looks like a big positive symbol, right? So anytime you have cation, you think positive ion. Generally speaking, if we think about metals, and if I draw out my makeshift periodic table really quickly here. Yeah, it looks kind of like that, okay? We know that the metals are on this side of the periodic table. Generally speaking, metals will want to lose electrons. When you lose electrons, you become positive. So more often than not, our metals will be positive ions. This is specifically for our ionic compounds. Okay, this will all make sense when we go to the next slide. We're actually going to start with molecular compounds, because I find it's a bit easier to name the molecular compounds. So the first thing we want to remember is what a molecular compound is. It is a nonmetal with another nonmetal. Okay, so again, if I draw my... I feel like I'm making this look worse every time. This goes like that, kind of. Okay. My nonmetals are on this side of the periodic table. Nonmetals. Okay. My ending always becomes ID. It doesn't matter what the compound is. Whatever element is there, the ending changes to IDE. Also note that these do not always have fixed ratios. Again, that'll make sense when we do some examples. So if I look at these two here, looking at my periodic table, I know that C is carbon and O is oxygen. I have one of each of those, right, in this example. So this will be carbon monoxide. Two things to keep in mind. First, I'm going to change that D because it looks not great. So, oxide instead of egen. And I also have mono here. Okay? Mono means one. I have one oxygen. Monoxide. If I wanted to name, let's draw that there. This one here. C is still carbon. That hasn't changed. There's still one carbon. But this is actually called dioxide. Let's keep in mind IDE. My ending has changed. Instead of oxygen, it's oxide. But I also have di. Di means two. And in this case, I have two oxygens. So carbon monoxide versus carbon dioxide. We name our molecular compounds using prefixes. Okay? Now this is something that goes before the name. It's right before. There's a set that we use. We're only going to go up to 10. You can do 11 and 12. Mono means 1. Di is 2. Tri is 3. Tetra is 4. Penta is 5. Hexa is 6. Hepta, 7. Octa 8. Nona 9. Deca 10. Now, you can think about shapes, right? Like a heptagon. Actually, I don't want to draw a heptagon. I'll draw an octagon. An octagon has 8 sides. Stop, just like a stop sign, right? Or a pentagon has 5 sides. Yeah, that's kind of a pentagon. Hexagon has 6. I can't draw odd shapes, so I'm not going to draw that one. But this chart, you're definitely going to want to keep in mind when you're naming your molecular compounds. This has nothing to do with ionic, though, okay? So I'll write ionic and put a line through it. Not ionic, only molecular. So if we look at some examples, first thing we want to do is identify the elements. So identify elements. And you'll always have your periodic table. I have mine in front of me here. N, nitrogen. O, oxygen. Alright. Another thing I have to keep in mind. Change. Ending. These are no good today. 2. I-D-E. See, that looks like icicle or icicle, I don't know. Try that again. I-D-E. I'm going to underline that as well. So, nitrogen, oxygen, it's actually going to be nitrogen oxide, but I got to keep in mind how many of each element I have. So, let me move this down there. Done. So, number using prefixes. And these are the prefixes that we want to remember. Okay. So I have N2O3. So N2, that would be di. Whoops. So dinitrogen. And 3 is tri. So let me make some space here. Oh, that didn't work. Let's try that once more. Trioxide. Dinitrogen trioxide. Right there. Alright? Now if I look at PBr3, using my periodic table, I'm going to find my P. It's not potassium, that's actually K, it's phosphorus. And Br is bromide, or bromine, but it will be bromide. Bride. That's not what I want. But I have to keep in mind I have a 3 here. So it's actually going to be phosphorus tribromide. Let me move that over. Phosphorus tribromide. We can also go the opposite direction. So instead of naming them, we can actually write out the formula. So phosphorus pentafluoride. Phosphorus I just wrote. I probably should pick a different example, but whatever. That's a P, capital. And I have pentafluoride. So that means I have 5 fluorine. I spell this wrong. But first thing I want to do is find the formula, or the atomic symbol for fluorine, which is F. So I have 2 options. I can either put the 5 here or the 5 here. But because I know it's pentafluoride and it means I have 5 fluorine, I want to put the 5 here. That's where the subscript belongs. And I'm just going to move this over so it looks a bit more appropriate. So there's my answer for that. And then finally, dinitrogen trioxide. Wait a minute, I just did that, didn't I? Bad example. And 2O3. Dinitrogen, 2 nitrogens, trioxide, 3 oxygens. Okay, naming ionic compounds now. Keep in mind these were all molecular. Now we're going to look at ionic. This does not use prefixes. Also want to keep in mind this is a metal plus a non-metal. Okay, the example I always go to is NaCl. This is table salt. What we're going to want to do is name the metal first. Okay, this is our cation. If you recall, if I go back here, cation, metals. See, I wasn't lying. And then the non-metal will be second, and this gets the IDE ending. Okay. Ionic compounds, one thing I want to make note of, these do not share electrons evenly. This will come up later in the video when we're drawing our diagrams. So Na is sodium, Cl is chlorine, but we're going to change that ending to IDE, and I'm actually going to write it here, chlorine. And let's use yellow to make it IDE. So it's sodium chloride. Next example, Mg is magnesium. And we have oxygen. But, because we have to change the ending, comes magnesium oxide. Last one here, I've got K and N. That's interesting, eh? K is the one that always throws people off. Potassium. And N is nitride. Well, N is actually nitrogen, so I'm going to write nitrogen. And then keep in mind the IDE ending. Nitride. Okay. So these cases are all pretty straightforward. But multivalent ions tend to be a bit more difficult. The reason for that is these are ions that have more than one charge. Good examples are iron, copper, lead, which is Pb. I forget what the charges of lead are, though. I can look that up afterwards. You will be able to find all of these on your periodic table. No, messed up that last line. This needs to go straight across. There you go. Yeah. Most of these are going to be in this area, in the transition metals. What we do is we use Roman numerals to write the names. And now Roman numerals are 1, 2, 3, 4, 5. Where am I going to write my 6? 6, etc. You don't need to know all the Roman numerals. That's pretty much good for now. We want to use the charge of the non-metal to find the charge of the metal. That's because these always have fixed ratios. Okay? The way we know that is the charges must balance. So we're going to do a couple of examples. So, first example, CuN. Well, Cu3N. Okay, I know Cu is copper. I know N is nitrogen. So my first step is to find the elements, and I've got them there. The ions for each element. Okay, I know copper has multiple ions. So copper could be copper 1. I should actually write it here. 1 plus 2 plus nitrogen. Okay, let's look at the periodic table. I know you can't really see it, but nitrogen's right here. Actually, let me write that out with blue. And we discussed last week, or in the last video, how to find our charges using our periodic table. So, group 18, this is 0, right? No charge needed. Group 17 will be a charge of -1. Group 16, -2. Group 15, -3. Nitrogen is actually the first element in group 15, so it's -3. We know for sure that nitrogen has a charge of 3-. Okay? If we look at our example here, Cu3N, it wouldn't make sense to use the 2 because there's no 2 subscript on our nitrogen. There is a 3 on our copper, and the way that works is, I'll actually write it out. You do a cross multiplying. So Cu becomes 3 because this 3 goes straight down there. And, well, there's nothing on the N, right? So that means the charge of copper must just be 1. So we know that we have copper 1. Therefore, I'm going to erase my periodic table here because I need the space. We know that the name is copper 1 nitride. If we do another example, will it make a bit more sense? FeCl3. Okay, elements. I know Fe is iron. And I know Cl is chlorine. Now, what are the ions for both of these? Fe, I'm pretty sure iron has 2 charges, 2 plus and 3 plus. So it could be 2 plus, 3 plus. I don't know, could have more. I'm not entirely sure, actually. Chlorine, however, again, if I look at my periodic table, probably spending way too much time drawing this out. I should just be pasting it each time. Anyways, chlorine is group 17. It's very reactive. It's a halogen. Group 17 has a charge of -1. So chlorine for sure is -1. And this is my non-metal. So if I check that charge, I have to be able to find out, or I have to have the charges balance out. So Fe question mark Cl1. I actually wrote CH here, my mistake. Let me erase that. Cl. So if I do my cross multiplying, I'll end up with Fe1. Cl has to have 3. So we're actually going to work backwards, and we know that this is Fe3. What does that all mean? When we write out the name, we know that this is iron 3 chloride. Okay? Charges must balance. The more you do this, the more examples you do, the more it makes sense. Let's do the last one, MgO. The elements are magnesium and oxygen. We know that for sure. The ions of both of them. Okay, magnesium is group 2, meaning it's 2+. Oxygen is group 16, meaning it's 2-. Okay, so if we do our cross multiplying trick here, MgO 2+, 2-, Mg2O2, we know in math these two can cancel out because they're the exact same. So this is just magnesium oxide. Sorry if that hand's in the way. I'll write it again over here. Magnesium oxide. Alrighty. Okay, drawing compounds. I'm into 20 minutes. I think I will go ahead and do it. One thing we want to recall is our valence shell electrons. These are the electrons on the outermost shell. So if we think about our BR diagrams, which was 2 videos ago, I believe. These electrons are involved in bonding, which is very important when we consider compounds because that's how compounds are made, with bonding, right? We also have to keep in mind this order of 2, 8, 8, 18. Elements, or atoms I should say, are balanced when they are at this level. Therefore, they are unreactive. And that's where they always want to be. Now, if we draw valence shell electrons on specific elements, so oxygen has, I believe, 6 valence shell electrons. So 1, 2, 3, 4, 5, 6. Carbon has 4. Hydrogen has 1. Sodium has 1. These are Lewis dot structures. And we use these to draw our compounds. Okay? So anytime we want to draw a compound, we have to keep these things in mind. Quick example. Water is always my go-to for this. Very simple. I have 2 hydrogens here. Okay? 2 multiplied by 1 valence shell electrons equal to 2. My oxygen has 6 valence shell electrons. And there's 1 oxygen, so that equals 6. So in total, I should see 8 electrons. Write it out there. I'm going to draw 1 oxygen here, 1 hydrogen here, 1 hydrogen here. I'm going to draw in my electrons on hydrogen. 1, 1. I'm going to draw in my 6 electrons on oxygen. 1, 2, 3, 4, 5, 6. What happens is these two will form a bond. And these two will form a bond. Let me draw that in yellow. Oxygen will have a slightly stronger pull on them. So what it will really look like is that electron will be closer to hydrogen than it will, or excuse me, closer to the oxygen than it will to the hydrogen. That makes hydrogen slightly negative, or slightly positive, and oxygen slightly negative. But that is what our H2O will look like. CO2 is going to be very similar, but slightly different, okay? And I'll explain that slight difference. We're going to start off the same way. Carbon has 4 electrons multiplied by 1. Oxygen has 6 valence shell electrons multiplied by 2. So it's going to equal 12. So in total, I should see 16 electrons. I start with my carbon in the middle, draw an oxygen here, and an oxygen here. My electrons for carbon, 1, 2, 3, 4. My electrons for oxygen, 1, 2, 3, 4, 5, 6. Let's put it there. 1, 2, 3, 4, 5, 6. Right now there's no bonds. Okay? Nothing is bonded on this, so it's not actually a compound. But what will happen is, if I get rid of those 2 electrons, I can put one of them here. So there's a bond there. If I can get those 2, put one of them here, so that's a pair. Now if I look at each electron, or each atom wants to have 8 electrons on it to have a full shell. So if I look at this oxygen here, 1, 2, 3, 4, 5, 6, 7. 7. That's not 8. This oxygen's going to be the same. Don't even need to count it. If I look at this carbon here, it has 1, 2, 3, 4, 5, 6. Something's wrong here. They're not balanced yet. So let's get rid of all that jazz. One thing that you've hopefully realized is that right now, that's a lone electron, that's a lone electron, that's a lone electron, that's a lone electron. Electrons do not want to be by themselves. They always want to be paired. So let's see if we can pair them up. Get rid of that. Get rid of that. Get rid of that. Get rid of that. Carbon's electron is still with carbon. Oxygen's electron is still with oxygen. But now we have 2 pairs. Let's count them up again. 1, 2, 3, 4, 5, 6, 7, 8. 8 there. This is going to be the same 8. Now if I look at carbon, how many electrons does carbon have? 1, 2, 3, 4, 5, 6, 7, 8. 8. So each one is good. Each one's happy. Now, how many should I see in total? Let me get rid of all that. When we wrote out, hold on a second. When we wrote it out initially, I said in total I should see 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're good. That is carbon dioxide. I'm actually going to stop it here because I'm at 27 minutes. 27 minutes, oh my god. Way too long. Most people haven't gotten this far yet. Sodium chloride and magnesium bromide. Why don't you try these? Try these, okay? And we'll connect in the next video. Until then, green on black looks pretty cool to me. Thank you. Have a wonderful evening.